Hi, everybody. OS, my honor and pleasure. Okay. It had a long, diverse, very long USC PhD, Carnegie Institute, Washington, during which you essentially invented laser flight.
Well, yeah. Zach Sharp invented.
That Oxford lecture for years, and then Ed has very diverse. But this talk is not an
There's things worse than isotope geochemistry.
So it's weighed in on many problems. The pumped isotope. Most recently, I'll spare you the details on that. Better at it, but essentially using telescope observation.
Yeah. Well, thank you. So, yeah, so there's not a single isotope in this whole talk. So I'm really sorry. Only because we can't measure them. We're out there. So yes, as Saku said, thank you. For about 15 years, I've been collaborating with astronomers and astrophysicists to try to understand whether or not we can use geochemical principles to say things about rocks outside of our solar system. This all began, and the beginning of my talk will begin with studies of polluted white dwarfs. There was a colleague of mine named Mike Jura at UCLA who was in the foundational to understanding that when you look at a white dwarf star, which is left over from our sun will be a white dwarf when it throws off its so-called planetary nebula when it's done. Those things are made of hydrogen and helium. If you see any element on the surfaces that's basically a big oxygen core, but with hydrogen and helium on the outside, if you see any elements on in those stars, they're not from the star because those all sank. They're too heavy, too big, floating in the hydrogen and helium. So if you see any elements, it's pollution. So we call them polluted white dwarfs. It's now been documented that pollution is rocks. It's composed of rocks. So we can look at element ratios in polluted white dwarf stars and do geochemistry. And that's what got me interested in this in the first place. We were looking at element ratios, and we started looking at the element ratios, and they looked like differentiation trends, igneous trends in stars. And we were looking at and trying to understand if we could really say something fundamental. So that wind forward another decade, then exoplanets comes online. Everybody's starting to get data on extrasolar planets. And again, there's the enticing prospect of doing geochemistry with exoplanets. And so all of this is I think, providing us the opportunity to put our Earth in a galactic context. How normal is Earth from a viewpoint of bulk composition? How normal is Earth from the viewpoint of structure? We all think we know what planets are. We think of planets as iron cores, silicate mantle, enriched silicate crust, and then an atmosphere. We think we understand planets. But what I'm going to try to tell you today is that may be an aberration is maybe too strong a word, but it's definitely a subset of what most planets are. It's not the typical structure. Okay, so and then before I even start, if I grew up as a petrologist, right? So we learn in petrology classes how to read ternary phase diagrams like that, like in sophomore year. But I'm guessing not everyone here knows how to read a ternary phase diagram. So I hate when people do this, but I have to take a sense of who knows how to read a ternary phase diagram. Oh, wow, okay. That's going to make the talk much faster. But I'll explain. Yeah, right. So if you wanted a graphical synopsis of my talk, this is how Earth got its water. I'm going to talk about that from the viewpoint of exoplanets. And that's a phase diagram for all planets, believe it or not, except for giant planets, all subgiant planets. Okay, so the first issue is bulk compositions, and this goes to the polluted white dwarf study. What are rocks like outside of our solar system? We use chondrites as the benchmark for rocky compositions on our solar system because, at least certainly at a log scale, and even at a fairly tight scale, if you're working with major elements, okay, people like to say the Earth is not chondritic exactly, but it's pretty close from an astronomical point of view. So basically, the rocks in the solar system are more or less chondrites. So the first question is that true elsewhere in the galaxy? And so to make the point very simple, I'm showing you a simplified diagram of the kinds of things that we measure with polluted white dwarfs. This is the log of iron to aluminum, log of silicon to aluminum as measured in white dwarf stars. And those elements have to be coming from rocks. It's a long story that I can talk to you about later, but there's really no other way that these elements could be on the surface of those stars. The white dots here are the white dwarfs, and then here's Earth, and here's Mars, and this is a probability density plot made, a heat map, if you like, for those points comprising the white dwarf. Now I'm just showing some of the very best characterized ones. The point of this slide is, the bullseye on the heat map is where Earth is, which is to say the polluted white dwarfs in aggregate look like rocks from our solar system. Now Mars is a little different. We wouldn't be able. They're not looking like Mercury, okay, for example, and they don't look like more crust. But we can, and this is a simplified diagram. I can make it more complicated by looking at the ratio of any of these elements like chromium, nickel, calcium, aluminum, magnesium, iron, ratio to magnesium. We always have to work with ratios, just like in geochemistry, ratios are more precise. In astronomy, ratios are more precise, right? So we always work with ratios. So here's a plot of the white dwarf ratio relative to the element to magnesium versus Ci chondrite. And then if these things look like Ci chondrite, statistically, they should be on a straight line 1-to-1, and then this is the reduced chi-square for that fit. So this is just showing you that this particular white dwarf is not a bad fit for bulk Earth. This is the reduced chi-square. It's not a great fit for bulk silicate Earth. It's a terrible fit for mean ocean ridge basalt, and it's an even worse fit for continental crust, which is we can tell that white dwarf has been polluted by rocks that are basically chondritic. And we can do this. This is an eye chart, I understand, but all you really need to see is the white ones versus the gray ones. The white ones pass the reduced chi-square test for being chondritic. And the gray panel, each one of these is a white dwarf star. And the gray panels are the rejections. And you can look at each one in detail, so you can say this one was rejected because the reduced chi-square is 4.8, 3.6, 3,000, whereas this is 1.7, 0.9, and so forth. And these are chromium, calcium, nickel, aluminum, silicon, iron, for the most part of the elements we're able to detect. There's others as well, and magnesium, of course. So my graduate student, Isabella Treeweiler, wrote a paper in 2023, and the paper is entitled The Chondritic Solar Neighborhood, because we could show that 60 to 70%, when the data are properly corrected, 60-70% of the polluted white dwarfs are basically chondritic. And then she applied the same thing to stars. And so there's a catalog called the Hypatia catalog that has a lot of the spectra of different stars fairly near to us in the galaxy. And long story short, the percent of these Hypatia stars that are chondritic, doing the same kind of technique, where it's not pollution, but it's just the elemental ratios in the stars, about 70% of them are chondritic. And when we look at the white dwarf data where we correct for steady state, meaning these elements can sink, and if they're in steady state and we do the correction, there's a slight change in the element ratios. 67.7% of those are chondritic. And then this is just an exercise in leaving. If there's one out, we found that there's one element, the siderophiles, iron in particular, create a problem in being chondritic. So the reason iron is a problem is because the galaxy has not been producing iron at the same rate over time. So this is a plot of iron over hydrogen, which is used by astronomers basically as a timeline. This is the overall metallicity of stars. Time is moving from left to right, and iron is used as a proxy for the total numbers of heavy elements. And on the y-axis of the plot on the left, I'm plotting magnesium versus hydrogen. Isabella is. Magnesium versus hydrogen. This is a stand-in for all rocky elements. This is an alpha nuclide like silicon and so forth. That's our stand-in for all rocky elements. And you can see the stars go like this, and then when you get to about minus 0.5 in metallicity, this is a log scale, the trend takes off a little bit to the right. Or plotting it a different way here, this is magnesium over iron, and you can see there's a dogleg. And that dogleg is the history in the galaxy when type 1a supernovae came online. And type 1a supernovae are transfer of material from one star to a white dwarf in a binary. And that cannot happen until stars age enough to throw out their outer portions and become a white dwarf. So it didn't happen right away. So this knee is when iron started to be produced prolifically by type 1a supernovae. So we can actually see that bend in the elemental ratios, and this is just showing us that this is a little technical, in terms of this is do not pass versus pass, and magnesium, iron, and just showing us the ones that do not pass tend to be dominant over here. And so the gist of that is we can make a probability density plot for what planets are likely to have 1/3 of their mass being an iron core, like our planet. Okay? And the high, when you're to the right of that knee, you do in fact get from the Hypatia catalog and the white dwarfs only with poorer precision, you do in fact get that the mean or the median, if you like, estimate of how much iron is in those planet building materials, the stars, corresponds to about 30%. So in other words, we expect planets made around those stars to have cores sort of like our Earth, total mass, because we're about 1/3 iron, right? However, if you're to the left of that knee, if you're over here, you don't have enough iron. So planets that formed early probably only had 20% of their mass could be made of an iron core. So the first two messages are rocks like everywhere. Chondrites are all over the galaxy. We can say statistically something like 60 to 70% of all the rocky materials or all the stars that will produce rocks have elemental ratios that are not distinguishable from chondrites with respect to the precision with which we can measure them. And we can say we expect those rocky things to have enough iron to make 30% by mass, 1/3 of their mass, an iron core, unless they're too old. Okay? So that's the first part about bolt composition. The next thing to think about, so that's rock. So I like to just sum it up by saying rocks are rocks. And fortunately, what we study in the solar system is relevant to everywhere. It looks like we have basic. So when we talk about cosmic abundances, which we do, when we talk about chondrites, we're actually right. They are cosmic. So planet demographics. The next thing is how typical is an Earth-like planet from the census of exoplanets that we're looking at today. Now, I can't answer this question, but in trying to answer the question, there's a lot of interesting things that come out. So the first thing to understand is when we look at extrasolar planets. Now, for the rest of the talk, when I talk about extrasolar planets, I'm leaving aside the ones that we first discovered, the hot Jupiters, big giant planets. Not interested in big balls of gas. I'm interested in things that have rock, or have the prospect of having a rocky core. So one way to refer to them is the Kepler planets, because they come mainly, the observations come from Kepler. So this is a plot of Kepler planets, if you like, planet size and Earth radii and orbital period. They like to do things in terms of orbital period. It's great for an astronomer. It's kind of annoying for a geologist because it's not really a parameter that's very geochemical. But it does allow you to look at the census, the statistics, the demographics. And one of the things you learn is that there are basically two kinds of planets that we see that are more massive than Earth, bearing in mind that seeing Earths is really hard because they're really small. But from the viewpoint of transits and being able to see the radii and estimate the masses, we're looking at things that are more massive than Earth, and they break up into two groups. Super Earths, which are down here, and sub-Neptunes, which are up here. Sub-Neptunes and super Earths are distinct, and they're both more massive than the Earth. There's different ways to look at this. Here's one of my own plots. These are plots of actual planet observations on a mass versus radius diagram. Each one of these data points gives you, for example, a bulk density, right? You have the mass, you have the size, you get a bulk density. Then I've tried to fill in between the points with a fictional set of samples, a KDE that's unweighted in this case. Just try to say, these, if this is hard to see, then you're going to weight it more heavily because you're not seeing all of them, right? So this is an attempt to correct for that. These happen to be a few famous exoplanets that we'll come back to. We can do the weighting in different ways and so forth, but this is what the demographics of these things look like. And basically, as I said, we break things up into sub-Neptunes. Let me go back here. Sub-Neptunes are up here, and the super-Earths are down here. And of course, Earth would be down here, planet mass of one Earth mass. So this is what we're dealing with: sub-Neptunes, super-Earths, and Earths. We don't find many Earths. There are some that are famous, but for the most part, sub-Neptunes and super-Earths. The observables are their bulk densities, their mass and radius, so we know their bulk density. Earth is 5.5, right, on that scale at grams per cc, or 5,500 SI units, and then we can compare the densities of these things to those, and we'll do that next. Now, before I say much more, I'd like to draw this analogy. In about 1925, nobody knew what the sun was made of. Cecilia Payne wrote her PhD thesis at Harvard, and she made this statement. She discovered that there was a ton of hydrogen and helium in the spectroscopy of the sun when she did proper quantum mechanical corrections. People had not done that before. And she wrote this sentence. She said, the outstanding discrepancies between the astrophysical and terrestrial abundances, meaning all the other rock-forming elements, are displayed for hydrogen and helium. The enormous abundance derived from these elements in the stellar atmosphere is almost certainly not real. In other words, she had discovered that the sun was mostly hydrogen and helium, but didn't believe it. But this is the seminal work that proved it. At the time, people thought that the sun was mostly iron, that there was a big iron core in the sun. I'm bringing this up because I think this is a very good analogy for where we are for most exoplanets, certainly the sub-Neptunes. We're just seeing this big ball with a density we do not know what it's made of. But it's super interesting to think about what it's made of, and can we use geochemical principles to try to tease out what it might be made of? I know it's flirting with fiction, right? I have a colleague who says, is this science? But it is science because we're using principles that I think are valid to try to make an hypothesis, trying to figure out what the sun is made of, planets. So let's go to the sub-Neptunes. The sub-Neptunes are the big puppy things. What do we know for sure? They have bulk densities of about 2 grams per centimeter instead of 5.5. If we assume that this planet is 2 grams per centimeter cubed, and we assume that its core is Earth-like, and to an astronomer, core means different than to a geophysicist. We often use the term core to mean everything that's not the atmosphere. I'm going to lapse into that, and I apologize. When I mean metal core, I'm going to say metal core. But when I say core, I mean everything that's not the outer envelope. So if we assume that it's an Earth-like core beneath some puffy thing, and if we assume that thing is water, then you could explain the sub-Neptunes as being composed of 40% H2O by mass. And this has been given a name. Bahudissalam at Cambridge has called them Haitian planets. There's a lot of literature on Haitian planets. And it's exciting, right, from an astrobiology point of view, because these are water worlds. So a lot of people want to take certain classes of sub-Neptunes and say that they're water worlds, and that would be cool, but it's just based on the bulk density. Now, mind you, Pluto only has 20% water if you think it's made of chondrite and ice. So making something out of 50% water by mass is a tall order. It's not impossible if you calculate Pluto, if you recalculate how much water it's made of, if you allow that it has 1/3 of its non-water part made of metal, then you can come out to about 50% by mass water. The rest of this is correcting for oxidation of iron, which makes sense. So the point here is Haitian worlds are a tall order, but not impossible to make. And it's an attempt to explain the bulk density of these planets. But there's an alternative. Well, okay, before I give you the alternative, there's a reason to want to search for an alternative. And that is that we've worked on a code, which we now call the Global Equilibrium Code, which takes equilibrium thermodynamics and asks the question, what would a planet look like if you allowed the whole thing to come to thermodynamic equilibrium? And when we apply that to models of planet formation, we can show that it turns out that the amount of water that you would actually get on the surface of a planet would be very small compared to the amount of water that you actually accrete, build the planet. So let's think asteroids. Wet asteroids collide together, they build a planet, you get a bunch of water, but then you allow the whole thing to come to chemical equilibrium, the water's gone. Why? The water goes to the core. Hydrogen goes to the metal core, and some H2O and H2 ends up in the silicate core. So you lose a ton of water. So we've done these models. We just published a paper on that. We've just revised our thermodynamics to take into account more non-ideality. So the plot actually looks a little more like this, but the basic conclusion remains the same, which is it's hard to build a water world. So there's an alternative to sub-Neptunes, and that is that they're gas-rich planets. That they have a core, but their outer atmosphere, if you like, or envelope, I call it an envelope because they can be supercritical. They're quite high pressure. They can be supercritical. But if you allow, again, that the planet is 2 grams per centimeter cubed, the core is like 5.5, and you take the density of H2, then it requires about 2.5% H2 envelope to explain a typical sub-Neptune. We're all becoming quite enamored with the idea that the sub-Neptunes are made of hydrogen atmosphere. Artist rendition. Why would they have hydrogen-rich atmospheres? Because now we know planet formation is faster than we used to think it was because of concepts like pebble accretion and so forth. We're building planets in the computer faster than we ever did before. We can build them on million-year timescales. This is a plot of the fraction of protoplanetary disks out there that still have hydrogen, and as a function of their age. What you can see is that the E-folding lifetime, or the time scale, if you like, for the lifetime of a protoplanetary disk is about 2.5. So while you're building planets in a hydrogen-rich environment in a protoplanetary disk. And you can do the math, and you can show that even when you get to Mars size, you're accreting you're accreting weight percent levels of hydrogen. If you don't do that, you need to find a way to stop it. Okay? It's not. This isn't like it's hard to do. This is expected. You should get hydrogen around these embryos, these planetary embryos, Mars size and greater. So hydrogen is part and parcel of building a planet. It's about disks. We'll ignore that. Now, my colleague Hilke Schlichting and other people working on the details of the populations of sub-Neptunes have shown that it's very likely that this radius gap between the super Earths, which have radii less than about 1.8 Earth radii, and the sub-Neptunes, which are about 2 or greater, that gap can be explained if many sub-Neptunes actually lose their hydrogen-rich atmospheres and they evolve to become the super-Earths. So she would argue, and many people around the world would argue, that super-Earths and sub-Neptunes actually represent a single population, but the super-Earths are more evolved. Yeah? So again, Hilke came to us and said, what is the equilibrium chemical state of a rocky planet with an H2-rich atmosphere, thinking about sub-Neptunes, that interacts with the core, meaning everything that's not the atmosphere? H2 is reducing, mantles are full of oxygen, so there's a lot of interesting redox chemistry that will go on if you play this game. Now the conditions, that's the other thing a geochemist has to come to grips with in this science, is the conditions are extreme. The plot we made. We lost the mic. These are the conditions. This is a model of the surface temperature beneath this hydrogen-rich atmosphere and the pressure In this case, where you lose the hydrogen atmosphere along a particular trajectory, and here where you don't lose it. And so what you learn is that you're going to get temperatures like 10,000 degrees and pressures of 20, 40, 60 GPa. These are massively extreme conditions. And the atmospheres are so dense, if they really are H2 atmospheres, the atmospheres are so dense and their opacities are so large that these magma ocean planets, because they're hot, can't cool very well. So you have a giant magma, one postulate is we have giant magma oceans covered with hydrogen envelopes, and the prospect for a lot of chemistry because the cores are molten. So the hydrogen can in-gas to the magma ocean and vice versa, and you get a lot of chemistry. Now, I didn't like making thermodynamic models at 40 GPa and 6,000 degrees because thermodynamic data don't go that high, which is why we're going to talk about ab initio molecular dynamics simulation, try to fill that gap. But also, at the end of the talk, you're going to see, thankfully, we only have to go to maybe 4,000 degrees and 4 GPa, much more comfortable, and I'll explain why. Okay, so magma ocean H2 interaction on a global scale. This is what I spent the last few years working on. And the idea was to replace what had been done in the astrophysical community up until a couple of years ago, which was what we like, and this isn't meant in a denigrating way, it's actually simple is good, right? But most of the inferences about what's happening between the magma ocean and the hydrogen had been papers based on one reaction, perhaps two. So these papers were about silicate reaction with H2, like metal, and very important reaction, but probably not everything. Other papers just talked about the solubility of H2 gas in the magma ocean, and the solubility of water. These are all really important. But our goal was to add more reactions and see if there's new things we could learn by adding more reactions to the data. So we did that. So just to give you a flavor for what we did, we do the linear, let's take a bunch of components in the melt. MgO, SiO2, MgSiO3, FeO, FeSiO3, and so forth. Oxygen in metal, silicon in metal, hydrogen in metal, as well as iron in metal, hydrogen and silicate, water and silicate. Throw all those together, we can derive a linearly independent set of reactions. This is important if you do kinetics in atmospheres. These are not kinetic reactions, equilibrium reactions, which means they are a basis set for your favorite reaction. And I bring that up because people who work in the mantle, they might say, I don't like this reaction. I want it to go a different way. My point to them is that that reaction is in there, and I'll tell you, because it is a basis set. Equilibrium, you can use a basis set rather than having to describe every reaction as it occurs. So anyway, we do the same thing for the atmosphere, bunch reactions, and then we do the same thing for solubility and evaporation, and we throw all those together, and we make and we solve the equilibrium conditions. Basically, find the free energy minimization point for all those reactions and all the mass balance points, and include the surface pressure as a constraint and solve that system. And I was telling someone earlier today, I did this in Python over COVID, and I'm terrible at this. So I make this Python code. It takes me 40 minutes to get a solution. I had colleagues at ETH who took my Python code and rewrote it in C, and it takes them about 15 seconds to get the same solution. So we're able to do a lot more with this code now. But anyway, but I just wanted to make the point. If your favorite reaction is MgSiO3 to 2/3 metal, MgO, this reaction isn't in there, it's because it's my reaction R3 for 2/3 R2. In other words, it's a vector space. And so you don't have to worry about the exact reaction, just to know if your basis set covers the full equilibrium thermodynamics. So what comes out of this? I could give a whole talk on this part. This is my little graphic for the chemistry that's going on in sub-Neptune. Let's say you have a metal core, you have silicate, you have hydrogen, there's all kind of reactions. Well, H2O is soluble, then the H2 can end up breaking up and make oxygen and hydrogen, metal, and the reverse of all that. There's a lot of chemistry going on that's really interesting. And the results are that you make water. You have a hot ball of oxygen, you put hydrogen on it, and make a ton of water. Planets are going to be wet. It's not, we shouldn't be asking how we get water. We should be asking how you could not have water on these planets. You have to have water on these planets. Also, H, O, and Si definitely go to metal cores if metal cores exist. So there's an auto-oxidation of the mantle, which puts FeO back into the mantle, which makes the oxygen fugacity that we report in our mantle, for example, high. There's a lot of redox chemistry, really interesting. How can we verify it? What we're doing these days is collecting spectra from planets, and it's their atmospheres. So you're seeing here data points for the spectrum of TOI 270b, collected by Benecke et al. And these model curves were an attempt to fit the data with our code, taking into account the elements other than hydrogen and helium that are in the gas. So SiO, for example, all these other things. Gas. And yes, you get a reasonable fit. Is it proof of anything? No. But it allows you to say that it's not implausible that beneath that atmosphere there's a magma ocean supplying heavy elements. That's the best observables we have other than the gas. So all that work on hydrogen and magma ocean, trying to understand, we saw redox chemistry, we saw making water. We started thinking, well, why doesn't this work for Earth? Why should Earth be, Earth does come into why would Earth be any different than these exoplanets from the viewpoint of the physical chemistry? There's no reason it would be. So we applied our model to Earth. This is a nice little graphic of it with the more detailed aspect of it. We imagined that the Earth is built from planetary embryos that were molten with hydrogen-rich atmospheres on them. Okay. We calculate how much hydrogen. And then we allow that same chemistry to just go on these protoplanets. And then those things assemble the Earth. And then what is the consequence of that? And the consequence of that is that we can explain several features of Earth just with this chemistry involving hydrogen. Now, in these plots, the white color represents the target, the true value for each of the parameters I'm showing here. So here, for example, is the density deficit in Earth's metal core. Density deficit somewhere between 7 and 10%. If it's 7%, and then and it forms at 50 GPa, when you compress it to 120 GPa, that 7% becomes 10%. 7 or 8% is a pretty good target for the formation. You will see if we started out with a mass fraction of hydrogen, 0.2%, and we take 3,000 degrees as the notional temperature of equilibration, because burning wood tells us that's what it is. Okay? We take that temperature, then the density deficit we get is voila, 7.8. Okay? We also make oceans worth of water, the process, but it turns out we can make 2 or 3 or 4 oceans worth of water when we take into account the non-ideality of the sense. And then we also get Earth's intrinsic oxygen fugacity, which is basically the amount of oxidized iron in the mantle. And we get the chemistry of the core, which just feeds into it. So this is just explaining to you that by allowing hydrogen to react with molten material in the proto-Earth material, we can explain Earth's water, Earth's density deficit in the core, and its intrinsic oxygen. So we think the Earth falls into this theme of hydrogen being integral to establishing the structure and chemistry. Okay, so now the phase equilibrium of planets with hydrogen. This is the part where we have to fill in what we don't know with physical chemistry. I have a colleague at UCLA, Lars Stickerud, who does ab initio molecular dynamics. And one of the first things he found when we started looking at this problem, and I have a student, Sarah Markham, who's also working on the problem, so these are actually her simulations, but guided by what Lars is doing. You can do two-phase molecular dynamics simulation, ab initio molecular dynamics. where you take MgSiO3, and in the computer you melt it at a certain pressure. You take hydrogen, take that up to the same pressure, and then you stitch the two together, let it run with time. You sort of like half femtosecond time steps, and you run it for maybe 20. When you do that, as an example, at 3000 Kelvin and 2.5 GPa, you run it with time, and not much happens. You make SiO molecules in the gas phase, which we expect. Make H2O molecules, which we expect. But basically, you still have two phases. You have a hydrogen-rich phase with some metals in it, have the liquid, right? If you do the same calculation at 4000 degrees and 3.5 GPa, you get one phase. They completely mix. So hydrogen and MgSiO3, which is our stand-in for molten rock, with MgSiO3, are completely miscible at conditions that are relevant for the surfaces that are between the magma ocean and the hydrogen in a completely miscible. So from a thermodynamic point of view, you can model that using asymmetric mixing model, subregular solution model. This is the free energy of the mixture of MgSiO3 and hydrogen. This is the mole fraction of hydrogen. This is the free energy surface that we calculate with the ab initio calculation, Lars calculation. And then this is a tie line that connects the two stable phases. The way this works is if you have a surface like that, you need to find a common tangent that hits 2 points on the surface. The 2 points of tangency give you the composition of two phases in equilibrium with each other. So this says, here we have a silicate magma that has a lot of hydrogen in it, and then we have hydrogen. And you do this at a series of different temperatures and pressures. Eventually, entropy wins, and this curve becomes just concave, and that's what you get, and then you have one phase. So I was really worried about this, thinking about hydrogen and melt, and I have another colleague, Edward Shovel, who said to me, well, if you threw the Earth into the sun, you'd have one phase. You know this is right at some level. Made me feel a little better. Okay, so here's a phase diagram, temperature versus mole fraction of hydrogen. This is a classic, if you're a mineralogist, this is a Solvis curve. If you're a chemist, it's a binodal. And the way you read this is, if you're above this curve, binodal, if you're above it, you have one phase. If you're below it, you have two phases. This is called the spinodal. Here you guaranteed to have two phases. Here you have two phases in equilibrium. Here you have two phases by spontaneous unmixing kinetically. So the way to read this diagram is if I'm above 3,500, 3,800 degrees at 4 GPa, I do not have a magma ocean and a hydrogen atmosphere. I have one phase. So this prompted us to write a paper saying, look, the way these planets work is not the way you think. I showed you those really high temperatures and pressures, a mass of hydrogen sitting on top of a magma ocean. That's not the way it works. It's one continuum, but then when you cross the binodal, now you have a surface. And that surface will evolve. It'll move with time. As the planet cools, it'll actually move in as it cools. So you have a surface that's moving slowly over billions of years as the planet cools. And that surface has conditions expressly codified by the binodal, 3,000 to 4,000 degrees. So we know those conditions. Another part of this is you put so many light elements in the metal becomes neutrally buoyant if it's there. And so you're not going to form a metal core because that metal is not like metal. We think of a ton of oxygen for hydrogen, less than metal by a lot. So this is a way to just if I get a horizon of metal, yes. I'm going to modify this even. So we had a postdoc, James Rogers, who's brilliant, took this and has done some very nice modeling to show the time evolution of such a planet. This is the old way of thinking about it. You have a fixed core, you have a hydrogen, and then over time the hydrogen leaks away, the core stays the same. In this new model, the core is fungible, if you like. It's evolving because the boundary is defined by a phase change in the planet, not by a material change. Phase change, like water to ice liquid. This is a complex diagram, but it's he made me a mug of this. We're very excited about this diagram. So this is pressure, temperature, mole fraction, H2. Everything under this hull is two-phase. Everything above the hull is one-phase. So we can build this into planet models and figure out what the structure of the planet is like based on this concept. But there's more. Okay? It's not like MgSiO3 and H2 are the only system where you have a binodal. We're talking very high temperatures. And I said entropy wins eventually. Entropy will make multiple phases one phase, throw the Earth into the sun. So it turns out if you take MgSiO3 melt and iron metal, and at very high temperatures, 9,000 degrees and 60 GPa, for example, they become one phase. And Lars had a student who actually did the detailed phase diagram for MgO-Fe, and then Sarah has done some quick calculations or some targeted calculations, if you like, for MgSO3 and Fe, and they tend to agree with the MgO. So we actually have a phase diagram, just like I showed you for MgSO3H2. We have one for MgSO3Fe. That becomes one phase. You're not going to get a metal core because the iron that would go in the metal core is dissolving in the silicate. And that's important because iron metal has a density of like 7, rock has a density of like 3.5, but when the iron goes into the silicate, we can't express that density. We can tell that because you can calculate the density. It's very much, actually, it makes the density slightly lower even because it's a little fatter. And then in addition, we know something about iron and H2 solubility of having a round-robin email fight with some mineral physics colleagues about what happens to hydrogen and iron at pressure. I'm absolutely convinced that the thing closes and solves this. Many other people are, but there are some mineral physicists who will tell you, no, there's a finite solubility of hydrogen in Fe, and that's it. But that's not true. And I'll tell you why it's not true. I'll show you in a phase diagram. But anyway, so we have this phase diagram constrained by what we know about this leg and the fact that it must close at very high temperature. So we have a binary, and a binary phase diagram. From that, we can make a ternary phase diagram. So this is the free energy of the ternary system, MgSiO3, Fe, hydrogen. And these are the interaction parameters for the non-ideality that leads to that closure. That's due to non-ideal mixing. One of these L parameters that we put in depends on composition. This is the full equation for the ternary mixing. From the full equation from ternary mixing, we can make a free energy surface. This surface, free energy surface in terms of hydrogen, MgSO3, Fe. We have that free energy surface. We can calculate that free energy surface as a function of temperature and pressure. I told several people this morning, I went to a meeting to show this, and I have an astrophysics colleague, he's Dulaman, came running up, these astrophysicists, he came running up and he said, I can make those diagrams. Because I was showing kind of shabby pylons. And Howard, why is he wanted to understand melted rock and protoplanetary disks, so he got himself all involved with phase equilibrium melts. And he came up with a method for calculating these tie lines based on the convex hull. These tie lines are basically a convex hull with this surface. So we're actually writing a paper and putting on GitHub this phase hull program to make these tie lines. Anyway, this is just the 3D version. Here I'm labeling it. So basically, the way you read these diagrams, I know that. So each tie line connects one phase to another phase at the equilibrium. Wherever you see a blue tie line, that's a two-phase region. So where the free energy surface goes like this, there's two phases in equilibrium. But when you're in the middle here, this is a one-phase region. How you read these diagrams, that's the most important thing. Where you see tie lines, it's two phases, and the two phases, the tie lines tell you what their compositions are. And so what I'm going to show you is a sequence of slices through this diagram at different temperatures and pressures. So here's one of those slices, just to get us oriented. This is MgSO3, Fe, and the H2. This region, how can you tell that's a two-phase region? Because it's got tie lines. The tie lines are connecting a metal-rich phase with hydrogen in it to a silicate-rich phase. Both have some hydrogen in them. Here's bulk Earth. Here's a typical sub-Neptune in mole percent hydrogen, and there's Neptune. We don't have a symbol for sub-Neptune. Made up a symbol for it. So there's a phase diagram. That happens to be at 5,000 degrees 13 feet. I actually made this one for the tool. It's not actually relevant exactly. You'll see relevant ones in a minute. It's cool because you have one of these liquids. You have an island of two-phase stability. It's kind of cool. You have two liquids. Similar, but not as much. That island is always kind of lurking in that. Anyway, so I think this phase diagram explains Earth as well as subneptune. So here's why. At 4,000 degrees and 135 GPa, which some people take to be, that's a notional value, right, for the core mantle boundary. So you have this phase diagram calculated at that scale. This is the bulk composition of the Earth in terms of hydrogen and silicate and iron that we calculated in our Nature paper. Earth sits here. The way to read this diagram is at these conditions, Earth would have in equilibrium a core with 10 mole percent hydrogen in it, half a weight percent hydrogen. And it would have silicate, mostly silicate. So to zero order, this phase diagram shows you the Earth is the way it is. It has an iron core that has some hydrogen in it. But if you added hydrogen to that system, this is where I think the mineral physics community works. If they work on systems that are Earth-like in composition, but when you add more hydrogen, our free energy surface tells you that you get more and more hydrogen in the metal, and eventually you get to a one-phase region. So this is sub-Neptune, and this is Earth, and they're at the same conditions with different hydrogen content. Does that make sense? I'll show you this nifty little animation of this diagram. Okay. This is just showing you. You could also do the same thing. If Bernie Wood's right and the metal and the silicate equilibrate at 3,000 degrees, 50 GPa, again, metal is here, silicate is here. But if you had more hydrogen, you'd be in a different two-phase region in those conditions. But both phases would be really. Okay. So I'm going to take you on a deep dive by virtue of the animation through a sub-Neptune so that we can look at how, as we go through the sub-Neptune, the phase compositions change, how the metal and the silicate and the hydrogen change. It's going to be pretty boring except for the first few seconds. So here's when you start, when you're hovering just above the magma ocean at the phase boundary, you are consisting of silicate, metal, and hydrogen gas, or envelope. You're in a three-phase triangle. And when I run this animation, this bulk composition of the Neptune is going to move down because we're going to be inside the core, diving through the core. So what's relevant is the bulk composition of the core. Okay. And then the diver, took me hours. The diver is going to track the depth. Okay, that matches this. So when you see the phase changes here, you can gauge how far you are in terms of depth. This is the surface of the magma ocean, the center, and this is 8/10 of the way. Okay. You run this thing. You watch the tie lines move. See the diver is moving. And boom, you're not even 9/10, you're not even 10% through the planet, and you're already one phase. So if you're a sub-Neptune, and you're in the core and you're diving through this thing, you're diving through one phase. Earth, mind you, down here at lower hydrogen cut, you're still two phase, you're still that earthy-like thing. So it's all about hydrogen cut. It's not just stability of things, it's about total hydrogen cut. Yeah? So this is going to go all the way to 400 GPa because that's when the diver gets. But now this is expanding out a little bit. but this is where the core is involved. Now, this is for 3% total hydrogen. Remember, I gave you 2.7 before. 3% hydrogen. Okay, there we are. So my wife said no one would understand the animation because the diver's going up. I said, look, pressure goes up. She said, yeah, the divers go down. So here it is again. This time the diver's going down. Watch it again. Cool stuff happens. Anyway, you see the diver. And then I put this here. If anyone wants to see, we can look at this and we can say, okay, if you want to watch it a little slower, right, we can sort of zip through. See, how can I do this? Yeah, I can zip through and then we can see, so you go from 3-phase to 2-phase, and then you're still 2-phase, 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 and then boom, yeah, you have 2 phases at 18 GPa, but those 2 phases are nothing like an iron. And then you keep going, and I could find it. Anyway, you get the point. Okay. Oh yeah. So now it turns out as the binodal shrinks and the planet moves in, the pressure of the binodal goes up. So I showed you one where the binodal was at 2 GPa. Here's a similar planet, but now we're going to start at 4 GPa, and I'm not going to run the animation, but I'll just show you that if you watch the little arrow on the right, you can see as we go through the planet, you're still, even when you start at 4 GPa, you're going to end up basically 1 phase very quickly as you go through the planet. Okay, so who cares? Last couple minutes. So I've worked for a long time making planet models based on these concepts. And on the right is a model of a sub-Neptune that is 6 Earth masses with 2% total hydrogen in it. And the density, the function of radial position, is on this map here. This is 1 phase interior. It's a dense atmosphere, and then it gets more. This is what we get. And for the radius of this planet, 5 Earth radii, the radius of the core part would be 1.988. A kind of classic sub-Neptune model looks more like the one on the left. I'm calculating the one on the left with an iron core, a typical mantle, and an atmosphere that is unreactive that just sits on the top. And for the same amount of hydrogen and the same total mass, the radius of this planet is 3.485. So it is not true that we know what the planets are made of based on their mass radius. This is a little deceptive because one of the reasons this is smaller radius than this one is because the molecular weight of the atmosphere is down here greater. So it's actually the atmosphere that shrinks more than the core in this model. So in order to expose the effect of the core, I made a model that's identical to that, but now I have an iron-rich core. It's not 1 phase. And that much less of a drastic change. This is the core radius is 1.82 instead of 8, so it's like 10% change. In any event, this is just but another degeneracy in trying to understand what's both there. Okay, very last 2 slides. Do they exist? So here's a plot of mass versus radius with a bunch of data from the Planetary Archive where we are filtering it for mass errors of less than 12%. And then I'm taking random draws of those planet models I just showed you, where the random draws can go up to 5% hydrogen. And then these are their cores, just the core part. And I'm trying to see whether or not lurking in this population of sub-Neptune planets on the high end above this curve, which represents pure rock, okay, lurking in here, could we be seeing these kinds of these miscible planets, let's call them? And perhaps so, because there's a huge literature on atmospheric loss of sub-Neptunes, which we won't try to go through here. But suffice to say, many of these things are losing their atmosphere. And so if you start with sub-Neptunes up here, they will evolve down here eventually. You take random draws from 2% to 5% population again, of course. And it's not crazy that they could be lurking in that population. Here's what happens when you confine your random draws to only 2%, something to 2%, here's the cores. Point is, these are actually ending up down where the super Earths are. So it could be that, and the super Earths, by the way, tend to be underdense relative to an Earth. So it could be that super Earths are underdense because they have all this hydrogen in their core. And that hydrogen may be in the core because they started out like these miscible planets. So anyway, this is just beginning, but we're trying to see whether or not the demographics of planets, not everything I just told you. These inclusions, bulk compositions of the rocky parts of planets are Earth-like, bulk compositions. Magma oceans can persist for DV-year timescales beneath H2-rich atmospheres, and there's a huge ramifications of that for physical chemistry of sub-Neptune, and even for protoplanets that built the Earth. And this chemistry is unfamiliar. It has very little to do with iron cores and mantles, very different chemistry. So when inferring interior structures from atmosphere observations, consider that these planets are not just one massive Earths. Whether or not sub-Neptunes are more abundant than Earths, we're trying to do completeness corrections for these planetary abundances. Nobody knows how to really do the corrections for the Earth-mass planets. So whether or not core formation is an aberration, demographic. So anyway, that's it.
I don't know why did I not see that?
Well, many of the lower mass ones will lose at Earth, but the larger ones will. So an awful lot of them become Earth. Some of them become super Earth by what's called boil off, almost it's some of them, so they're all evolving on different times. A lot of studies on it. I think Roger. So if you want to know, you have to read those papers. With your questions. But, I mean, I also have similar questions. What prevents more of them being little? They can model. This is the actual population. This Akash Gupta was a student of Hilke's. This is his model based on their atmospheric mass. They can reproduce the population based on their atmosphere. That include pi. I'm sure I'm not doing it justice. They can. Yeah, there's a woman named Eva Lee who's an astronomer at San Diego, who is one of the who wrote one of the first papers about how accretion works, very knowledgeable. She's developed an accretion only model that can produce sub-Neptunes and super Earths just as a result of the mass of scaling. That paper's out there and viable counterpart. They have all the atmosphere lost people who tend to be really fixated on the atmosphere, and I would say they're winning the fight at the moment. So they think that mass loss is right. One of the reasons they think that is because this slope of this gap with period is really important. And you need something that can. So now Eve says she can reproduce that slope to the peak. So there is a counterpoint. Is it all unified? She thinks it's. She worked with Eugene Chang. There's a very famous paper by Li and Chang, which is called "Coolest to Accrete." they developed the point that as a planet cools, it shrinks, but the hydrogen that's in the protoplanetary disk is going to want to fill up the Hill sphere, the sphere of gravitational influence around it. So as it shrinks, more hydrogen comes in. That's the accretion part. They worked all that out. He has some variant of that. But Hilke scares me. Yeah.
Go ahead. That like that the model can explain that what are the my question is kind of like I saw the difference water and contract.
Yes.
So that's the
Yes. So in our nature paper, we wrote a long appendix about that question. First thing I will say, nobody. Well, I don't think you should throw out every model that came. I'll be honest. The second thing I'll say is, I think that the difference in DH between water on Earth and water versus the sun has been overemphasized for this reason. Anytime you take hydrogen atoms, take them from H2 gas into water molecules, water is isotopic. Now you have vibrations. Those vibrations want to reach minimum. The water is always massively isotopically heavy relative to hydrogen. And it's not a fingerprint of where the water is. It's just that it's water. So people look at comets and they say, well, comets are high. The Earth's water must have come from comets. Really, it just means water in comets is water. Okay? So, and the same thing with asteroids. And the same, I mean, if you look at water in molecular clouds, they're highly deuterated. Water everywhere, highly deuterated. What's our model? So, turns out the difference in D to H between Earth's ocean and sun is about the equilibrium fractionation. You see, well, there's nothing room temperature about it. But one possibility, we argued, is that the upper atmosphere E to H exchange is accommodated by radicals. And radical chemistry is many orders of magnitude faster than so if you allow the D to H to exchange by radicals in the upper atmosphere that are roughly, will then make water that rains out not reset by equilibrium. Still 1,000, 2,000, 2,000. Orders of magnitude. So we did a nice little model looking at the different weights of gas. Equilibrium rate. Cringing all the time. Did I answer it? Well, that's fine.
There's one, though.
Yeah, so you do models over a bunch of conditions, kind of map out so where the phase change is. How do you know they're right? It's sort of like doing kinetic reactions in the laboratory. You run the models for a amount of time, get a result, and you say, well, if I run it longer, does it change? Longer, just run them for a long time. And things start, you do autocorrelation analysis. That all the bond distances and everything are calming down to a steady state. So you look for it, like in the laboratory, you look for a steady state. And proving that it's a steady state, and you're assuming that the steady state represents equilibrium. You try to demonstrate that it's equilibrium. So, for example, the models I showed you that Sarah ran were for 10 picoseconds simulations. Lars submitted his paper on the equilibration. Nature, come out, I think, soon, but he had to run it out to 60 people just to prove to a reviewer that it's not going to change. And that's hard. It takes a long time. So most of these have initial calculations. Run longer, especially the reason it's important to run longer for hydrogen. You have to use smaller time steps. Because hydrogen is so light, stick it around and capture the ocean. Capturing it. They put a lot of effort into figuring out how small the time steps. But I should also say that that's for the 2 phase. For the 1 phase, a lot of this stuff has been done for Earth's mantle quite successful. I mean, we have a lot of success. Like Laura have a lot of success. Still calculating. Agreed that melts are the next 2 phases. The next